Hello, and welcome to Distributed Learning of Optimal Controls for Linear Systems. My name is Federico Celli, and I'm a third-year PhD student at the University of California at Riverside. This is a joint collaboration with Professor Giacomo Baggio at the University of Padova in Italy and Professor Fabio Pasqualetti, who is my advisor here at UCR. As you know, networks are a popular way to model the complex behavior that emerges from the interaction among otherwise simple units. Today, we will be using a network evolving according to a linear time-invariant dynamics with state matrix A and input matrix B, and where we assume that some nodes in the system have control authority on the overall network. This control action is what we ultimately wish to design. We can use networks to model complex systems from the US power grid to the human brain. In this example, you can picture the state of the nodes V to capture the firing rates of a region of neurons, and the edges E to be the connectivity tissue among these regions. Given the complex dynamics that we are trying to capture, it is usually the case that a model of the system is not known, and therefore matrices A and B are not given. So how can we design a control action for a system with unknown dynamics? When a model of the system is not known, in a classical framework, a control scientist would either use first principles in order to synthesize a model of the system, or use data to identify the model. The model can then be used to design a controller. This latter approach is what we call indirect data-driven control. A different approach, however, consists in bypassing the identification step altogether and therefore using data to directly design a controller. This is called direct data-driven control. It is up to debate whether one method should be preferred over the other, and this discussion is not the focus of this work. However, in a recent paper, the authors compare direct and indirect data-driven controls and come to the conclusion that neither approach is invariably superior and that the choice of design must in practice be informed by the available data. In the remainder of this presentation, I will focus on a strategy to compute a direct data-driven control in a distributed fashion. For our problem setup, we are considering a network made up of capital M subsystems, each composed by an arbitrary number of nodes. Here in blue, I'm highlighting as an example subsystem 1, which is made up of 2 nodes, and one of which receives control input U1. Notation-wise, we let the block diagonal entries of matrix A be the subsystem's dynamics. For example, the blue subsystem internal dynamics is described by A11. The off-diagonal entries of A are the intra-subsystem connection. And as usual, we let B capture how the inputs are fed into the system. Another important aspect is how data is collected. In this framework, we run a total of capital N experiments, each of length T. These experiments, of course, involve the full dynamics of the interconnected systems, but we allow each subsystem to gather only data that refers to itself. That is, subsystem I has historical data X, U, and Y sub I, referring to all experiments N, but initially has no knowledge of what was recorded by other subsystems or the control actions that they received. And by the way, here X will refer to the state evolution, U will refer to the inputs, and Y will refer to the final state of any experiment. Ultimately, what we wish to find is a control action which globally minimizes a quadratic cost function in the states X and inputs U, compatible with the system dynamics, and constrained to drive each subsystem to a desired final state X of F, which we can see highlighted in blue. Once again, however, we can't use a model of our system dynamics, and in place of that, we will instead use the data that we previously gathered. In the paper, we give a few different formulas to find a data-driven solution to this problem when the data is shared among the agents. From now on, we indicate with U star of T the solution of this LQ problem. Among the different strategies that we use, I will focus today on a particular one, since it will serve as the foundation for the distributed algorithm later on. This is one of the auxiliary problems that we discuss in the paper. Notice how we arrange the cost function and the equality constraint of the original problem, where now we solve for vectors alpha, v, and w. Also notice that we had to introduce a tunable parameter epsilon. In a nutshell, the reason for this is that in order to distribute this computation, we require the constraint matrix to be full rank, which is the case here. In the paper, we show that when matrices U are full row rank, then multiplying the input data matrix U by alpha star will converge to U star T as epsilon approaches 0. On top of this, we're also able to find the approximation error for a control action as epsilon changes. Although the expression is rather long, hopefully you can notice how the approximation error formula depends only on data alone, so we don't need a model for this. So, how can we finally distribute this problem among all subsystems in the network? In practice, we let each subsystem create an instance of this problem based only on the locally available data, that is, matrices Y, U, and X sub I. We call this matrix W sub I. The first step in our algorithm is to initiate vector Z hat with the best solution that each node can find with the limited information available. This solution would be feasible and even optimal if subsystem I was operating alone in a vacuum, which is definitely not the case here. So this initial solution Z hat needs to be improved with data from other subsystems. The second step for the algorithm is therefore to start sharing some data among the subsystems. But instead of sharing matrices W sub I, which contains the full database of each subsystem, we share K sub I, which is its null space. Also, we share our current value of Z hat, and we receive matrix K and Z hat from the neighboring agents of I. I want to stress again that sensible data, such as the state evolution and the desired final state, is not shared among the agents, and the data collected during the experiments is in fact kept private. Yet, in step 3, we update Z hat with the information coming from neighboring agents, and the update law that we design allows us to find a vector Z hat which not only solves the problem for subsystem I, but also for all of its neighbors. By iterating through steps 2 and 3, we update Z hat every time with data coming from the neighbors of I, then the neighbors of I, and so on. Ultimately, we're able to show that if the network G is connected, then the estimate alpha hat of each subsystem converges to the centralized solution, and that the number of the steps needed to reach the solution is upper bounded by the diameter of the network. Therefore, this algorithm converges in a finite number of steps, whereas most distributed algorithms converge asymptotically. Also, the suboptimality gap delta can be tuned from a data-driven expression and is in general known a priori. Finally, here is an example of the performance of this algorithm. This network is made up of 6 subsystems, adding up to a total of 24 nodes and 14 inputs, and has diameter 3. On the right, we show in blue the performance of the algorithm, and we notice how the optimality and feasibility error reach 0 after 3 iterations of the algorithm, equal to the diameter of the network. Keeping the same subsystem structure, but changing their connectivity, we now have a network with diameter 5. Accordingly, we can see that the convergence of the algorithm, which reaches the optimal solution after 5 iterations. In conclusion, in this video we ran a series of experiments in order to design a direct data-driven control, which is distributed among agents of a network and optimizes a quadratic cost function with a constraint on the final state of the system. It does so in a finite number of iterations and with a suboptimality gap which can be known and tuned with data. We are currently investigating the performance of this approach when data is subject to noise or is injected with adversarial attacks. I hope that you found this video interesting and informative. And let me conclude by thanking and acknowledging the work and support of my collaborators. You can find more information about this work and many other topics in data-driven controls on our website. Ciao!